Well, thank you, Tom. I think Tom and I got the last two positions in the epidemiology session, two big sessions. Sit back, don't take photos, just concentrate what I'm talking about. Tom had a big session. In 10 minutes, I'd like to go for a quick tour over 2,500 years of Western philosophical thinking about cause and effect. So my name's Mark Burgemeister. I'm a veterinarian, a Buiatrician and epidemiologist from Shepparton, Victoria. And I've had an interest in how I know what causes things for a long time. So we think causally. In life, we learn very quickly through our life to think of causes and how we can influence them. We learn to work out very quickly what we can do to get what we want. In business, we learn to find out what causes what our clients want so they're happy. We think causally in life. When we come to epidemiology conferences and Buiatrics conferences, we speak in the language of Fisher, Neyman and Pearson. In the background is the Reverend Thomas Bayes. I would argue we think in a Bayesian way. Here, we speak in the language of these scientists. Oh, I'm not sure why it's wobbling. And that speaks in the language of measures of effect. The difficulty in the English language is a measure of effect gives us no indication of cause. A measure of causal effect is only a slightly different sentence, but totally different philosophically. Because in our textbooks we hear the phrase, association is not causation, and then we continue on. To me it's like, alcohol can harm you, have another beer. It's like we continue forgetting the fact that we've just said we can't predict causation. And the issue is the language we have shared between us can't help us with this issue. By the way, I have many references here. Come and speak to me after. I have the full reference list. You can reconstruct this conversation from the list. Inferential statistics, I want to highlight, is the language of association, not causation. This is not so much a presentation as a call for change, as a call for us to do things differently, as a call for us to change the way we speak, the way we are spoken to and the way we listen. Because this is a human paper about non-alcoholic fatty liver disease. If we were truly looking at association, it would lead us to say things like, these observations raise concern about the potential need for a heightened emphasis. Perhaps these authors have truly got what they can say from their work. And I am wanting all of us as listeners to be cautious about how we interpret scientific results when they are presented to us. My presentation is based on the work of the computer scientist Professor Judea Pearl. His work is instrumental in bringing in Western philosophy what has been a problem for 2,500 years. How do we know what causes something? And his work is on how do we communicate causality, because our statistical nomenclature can't. And Bayesian or frequentist probabilistic I'm putting together as both they can't. I will argue that frequentist probabilistic thinking is Bayesian thinking where the prior probabilities are non-informative. So I can answer that question. None of the language, none of the symbols can answer what is the cause. Professor Judea Pearl suggests the way we can infer causation is through use of a directed acyclic graph. A DAG, which to New Zealanders and Australians has another meaning, but here it's a directed acyclic graph. And I want to show you, and remembering that a graph is a mathematical method of communication, over the door of Plato's Academy it said, let no one ignorant of geometry enter here. And a graph is a method of communication in mathematics that we don't use enough. So here, this is an example DAG where A causes O the outcome. And I can draw A causes B and B causes O. Or it goes this way in the path, or this. It doesn't matter what A, B, and it's just an example in this one. What makes it directed is the arrows at one direction. A directed acyclic graph has single direction arrows. It is acyclic because there is no way you can return to the initial cause. This is different from other causal path models. It does not have feedback loops. It does not have other systems. You cannot return from the cause back, from the outcome back to the cause. I will now show you some examples of DAGs. Oh, this is the highlight. A DAG is a visual snapshot of an opinion. I'll come back to that. It is my opinion or the author's opinion of what causes something. Here is a simple DAG for bovine respiratory disease. Breed causes BRD. Breed causes a change in weight, which causes BRD. It's a simple one. Here's an intermediate one where the outcome is at the base. These are the causes, this is the path. A DAG is a method of communicating my opinion about what causes something to occur. It is only my opinion. What we have to get used to as listeners is it might not be yours, but a graph is the quickest way to show you my opinion. A picture says 1,000 words. It just depends which 1,000. This is a complex DAG. I need to highlight here that the freeware programs that produce DAGs are not made for PowerPoint. These are often best printed or shown on bigger pieces of paper when they go into such complex models. Having a perfect DAG, presenting the perfect DAG is not the key. The key is for me to show you what I'm thinking, what I thought caused an outcome at the start. The objective is not to pick faults in a DAG, it is to be able to see what my thoughts were in the DAG. We need to think carefully as listeners about how to interpret them. So DAGs are very important when the experiment is being designed because drawing a DAG outlines what factors need to be measured. It's a key way to work out what things do I need to measure, what things affect the outcome. The other side I'm discussing with you is when you see the DAG from my experiment, it enables you to see what I was thinking, what I was able to measure, what things I thought were important, and what things you think I should have included that I didn't. It is a communication tool, the DAG. Because if you can't see my DAG, you can't see what I was thinking. You can't see why I chose those things to measure and why I didn't include the others. You can't see in my part of the world what caused the disease and hence what in yours might be another cause. It's very important to show a DAG. These are all the same words. People condition, control, adjust or correct for confounders. The language of DAGs is condition, conditional probability. It is the best way to say it. When I hear I have corrected for confounders, I can't tell which confounders unless I've seen a DAG. A DAG shows you what confounders have been corrected. You can only correct for confounders if they're in the model. If they're not in the model, it's not corrected for them. That's why DAGs are so important. This is a DAG where I have no disease because I want you to think about something. Here is our outcome of interest. Here are some factors which are very proximate to the outcome. For example, mastitis at calving. These might be temperature at calving, time of calving, conditions at calving. And these issues, these causes are further back. They are more distal. The problem when we don't see a DAG is we can be dragged into being prisoners of the proximate. We think only of the factors that were measured, only of those things that occurred just before the outcome of interest. Showing a DAG with calving mastitis could link you back to heifer growth, conditions at insemination. A DAG opens up the thinking and reduces the chance of us being prisoners of the proximate. So in summary, I wanted to quickly talk about DAGs is something I'm calling for in our presentations to help us appraise complex information. They're a very quick way to see what people were thinking and how we can ask them about their thinking. To think causally with a wider view of complexity, we need DAGs to summarise that information and to reduce the risk of coming to spurious conclusions, a DAG shows us what people considered, what they measured and how they analysed, and how they could come to their conclusions of cause and effect. So I'm calling for more DAGs in our presentations at Buiatrix. And I'm hoping that over the thousands of years, at last we've come to something that could help us to understand the causes of things. All the references are here printed for you. Come and talk to me, or at my poster station I'm having lots of people talking about p-values and confidence intervals, which is a similar interesting issue. Thank you, Mrs. Chair.